So welcome everyone. Thanks again to Ankur Moitra from MIT, who we are lucky to have as a speaker in our bootcamp. He'll be telling us about recent advances in high dimensional learning. Take it away, Ankur.
Great, thanks so much for the introduction and again for the invitation to speak. So, last time what I told you about was I told you about tensor decompositions, and I think there'll be a little bit of an ebb and a flow to these lectures because last time I gave you hope. I told you about simple algorithms for tensor decompositions, and I told you about how you can take lots of probabilistic models and you can find low-rank tensor structure within them, mostly through trying to find variables that are conditionally independent, and how you can use uniqueness properties of the tensor decomposition as a method to perform parameter learning. But there's a dirty secret behind those kinds of methods and that general viewpoint, which is that you don't really believe that your data actually comes from such a simple generative model. At best, it's close to one of those generative models. So in this lecture, we're going to ask this tough question, what happens in generative models when our data isn't exactly from that generative model? And we're going to think about notions of robustness. So are there algorithms now that can actually tolerate some amount of misspecification in your model? Now, one of the nice things is that tensor methods are again going to play a key role, but let me start where it's always good to start at the beginning. So let me first start off with one-dimensional problems before we get to high-dimensional problems, and let's not worry about robustness just yet. So let me tell you about parametric statistics. And this is just a way of looking at things. It's a way of looking at generative models and thinking about how do you perform estimation. So imagine that you're given samples from some unknown distribution, but you know that it lives in some nice class of distributions. So one canonical example that we'll use throughout this talk is the notion of a Gaussian. So imagine you know your samples come from a Gaussian, but you don't know the underlying mean mu and the underlying variance sigma squared. And the basic question in parametric statistics is, can we accurately estimate the underlying parameters from samples? Now, this is a kind of obvious answer. The answer is duh, yes. Because in fact, what you can do is the obvious thing. You can take the empirical mean and the empirical variance. So the empirical mean very quickly converges to the true unknown mean mu. And the empirical variance, so x bar is the empirical mean, and you can compute the empirical variance, and that's very quickly going to converge to the unknown variance sigma squared. In fact, these two estimators, the empirical mean and the empirical variance, are two examples of a more general paradigm within statistics, which is immensely powerful. It's due to Fisher back in the early 1900s, who pioneered the idea of maximum likelihood estimation. So you look for the parameters that are the most likely to have generated the data that you observe. And there are a lot of wonderful properties about the maximum likelihood estimator that are known. You need some kind of technical conditions, but under the appropriate technical conditions, you can prove that not only does the maximum likelihood estimator converge to the true parameters, but it actually does so at the asymptotically fastest possible rate. That when you fix the estimator and send the number of samples to infinity, not only does it converge, but the amount by which it's wrong is the best possible in a sense. Now, one of the big problems with the maximum likelihood estimator is that it's not necessarily computationally efficient to actually compute the thing. And that's a major reason why last lecture we were talking about tensor methods and the method of moments, because those led to estimators that we really could compute. So we weren't trying to get the asymptotically efficient estimator. We were merely trying to get a good estimator that was computable in polynomial time. But really, I'm going to talk about another branch of this story, which it's a basic question that was introduced by John Tukey in the 1960s. And it's a question that's so fundamental that really it could have been asked much earlier, but it wasn't. And Tukey's work really led to, an entire field called robust statistics. So he asked, what about errors in the model itself? So what happens if your data doesn't come exactly from a nice distribution? It merely comes from a distribution that's close to a nice one. So here's the canonical way that you set up these problems. Let's go back to our favorite example. Imagine that we have a 1D Gaussian, and that's our ideal model. But the trouble is that our observed model, the thing that we're actually getting samples from, isn't exactly Gaussian. At best, it kind of resembles a Gaussian if you squint at it. So what we can think about is adding some type of noise on top of the distribution, and that leads itself to our observed model. And the question is, what can we do in the face of this noise? Is there a sense in which we can still meaningfully estimate the underlying parameters? So let me make this question precise, because we need to really mathematize this question to make sure that it makes sense when we go to high dimensions especially. But in order to formalize this question, one of the first questions I have to answer is, how do we constrain the noise? Now, there are actually many ways of thinking about how you could constrain the noise, and these are helpful ways to go back and forth between. So one way is that you can take that little twiddle that I showed you on the previous slide, which really describes the difference in the two PDF functions. One PDF being the idealized model and the other one being the observed model. And you could think about constraining the L1 norm of this noise. You could constrain the L1 norm, it's at most O of epsilon, let's say. Another way to think about this is you can think about it with an adversary. So if you overlay these two PDFs, the idealized model and the observed model, then you can think about the region in between these blue and green curves. And that's the place where the adversary is either deleting or adding points. So you can also think about this noise model as you take samples from some nice distribution, but an adversary gets to corrupt an O of epsilon fraction of the samples in expectation. So there's actually some subtleties to how exactly you define an adversary. So for example, there's Huber's contamination model, where you think about an adversary as just adding a fraction of the samples. This model I'm describing here allows the adversary to add and delete samples. And actually, the truth is we're going to work with an even more general model, where the adversary is allowed to look at the samples drawn from the idealized model and then get to decide what samples he wants to corrupt. Now, the distinctions between these noise models won't be very significant in this talk. I just mentioned it just to let you know. And you can think about it in whichever of these noise models makes the most sense to you. Now, let me lastly introduce a little bit of nomenclature that's going to be helpful for us. Oh, I already see a question in the Q&A. Are these two models in the slide equivalent? So they sort of are, but that's why I said arbitrarily corrupt an epsilon fraction of the samples in expectation. So actually, these two models are equivalent when the adversary has a budget and expectation of the fraction of things that he can corrupt, and his corruption strategy is actually oblivious to the samples that you observe. Okay, so in any case, you can think about it in the simplest model if you want, but let me introduce some helpful nomenclature that we're going to rely on throughout this talk. I'll think about the outliers as being the points that the adversary has corrupted, and the inliers as being the points that he hasn't. So this is our model for noise. This is what the adversary can do to move us away from an idealized model. Now, the remaining thing that I have to address is, what does it mean to estimate the parameters accurately in the face of noise? So in what norm do we want our parameters to be close? Now, the truth is that in one dimension, there are a lot of norms which are equally good as each other. Which one you choose doesn't really matter. But in high dimensions, it really does matter that you choose the right norm, that your problem actually makes sense. So let me go with the natural one, which is going to generalize the high dimensions much easier. So there's the notion of the total variation distance. That's just half of the L1 distance between the two PDFs, and it's defined in this formula. And the important thing to think about is that, what is our observed distribution? Well, it's any old distribution that's close in total variation distance to the idealized model. So we're given samples from a distribution that's epsilon close in TV to an unknown Gaussian. So we should try and use the same norm to define what it means to have good estimates of the underlying parameters. So what we want is, we want to output another 1D Gaussian, that's this orange curve, with the property that its mean and variance are close enough to what we started out from, that the orange curve is close to the blue curve in total variation distance. So the adversary presents you with samples from a distribution that's epsilon close to Gaussian in total variation. And what you want to do is, you want to find your own Gaussian that's 3 epsilon close to the Gaussian that you started from. So that's the setup for this problem. And you can also think about it another way, which is that noise isn't always bad. It's not something you're necessarily trying to remove. A lot of times when you're faced with data, the truth is that the samples you're given aren't from a nice model like a Gaussian. So you can think about it as, given the promise that there is a 1D Gaussian that really closely fits your observed distribution, can you find one that actually is roughly as close as possible? So these are the different ways to think about how I've framed the problem. This is how robust statistics traditionally frames these things. And now the next natural question you might have is, well, in the context of maximum likelihood estimation and estimating the unknown mean and variance of an actual Gaussian, we knew that the empirical mean and empirical variance worked. That's what Fisher's theory told us. So do these work in the presence of corruptions? And so here the answer is a resounding no. So if you think about it for a few moments, you'll come up with a pretty easy way to badly derail the empirical mean and empirical variance. So what would the adversary do? They could add a bump in the PDF that's way out in the tails. So we end up with this observed model right over here. It looks mostly like a Gaussian, but it has a little bump way out in the tails. And the problem with this now is that when you take samples from your observed model, well, its true mean is arbitrarily far away as you move the bump further and further away from the true mean you're trying to estimate. So both the empirical mean and empirical variance are going to go to infinity as you send this bump out to infinity. Okay, so there's a question. You don't care about actually identifying the corrupted points, right? That is exactly correct. So I'll discuss this a little bit more because I want to reveal this in waves. But indeed, here we're just talking about estimating the parameters well, and I don't necessarily care about identifying which points have been corrupted. One of the reasons why I'm framing it this way is because it's not always possible to identify which points have been corrupted. The adversary might not do something obvious like putting a bump way out in the tails. They might put it in the middle of the distribution, in which case it might be statistically impossible to actually tell which points are inliers and outliers. Instead, what I want to do is I want to identify the outliers that are really far out there in so much as they derail my estimator. Why 3 epsilon? Because it's an arbitrary constant that I'm not going to care about. Okay, so let's move on. So what should work instead of the empirical mean and empirical variance? So in fact, many of you will immediately be able to guess the answer, that instead of using the empirical mean, what you should use is you should use the empirical median. Because when an adversary adds this bump way out in the tails, well, it may pull the mean very far away from the original mean, but it's not going to pull the median too far out. And in fact, if the median works instead of the mean, what should you do for the variance? Well, you just use the median twice. So you can work with something called the median absolute deviation, which what you do is you take the median of your data and you take the absolute values of x1 minus the median, and you take the median of those things. And that gives you some rough estimate for the scale of your distribution. So there's another question, which is data poisoning included in these noise models, or it's conceptually very distinct? Actually, this is literally a data poisoning model. So I'll discuss some downstream applications in modern machine learning later, but these are all different terms for the same thing: adversaries, robust statistics, data poisoning models. And in fact, I'll introduce even more nomenclature to connect it to some classic TCS topics later. All right, so in fact, what's a folklore theorem in robust statistics? In fact, this theorem is so ingrained into the DNA of robust statistics that the truth is I don't even know who proved this theorem first, but it's very clear that many people knew this. So here's what you can show is good about the empirical median and the empirical median absolute deviation, is that it's provably robust. So given samples from any distribution that's epsilon close in total variation distance to a 1D Gaussian, the median and median absolute deviation, if you run them, and you spit out the parameters mu hat and sigma hat, then in fact, those will be such good estimates that the total variation distance between the unknown Gaussian that happened pre-corruption and the one that's defined by your mean and variance estimates will be O of epsilon. So you started off with something that's epsilon close to a 1D Gaussian, and you ended up with an actual Gaussian that's 3 epsilon close to the one that you started from. Now, just some minor technicalities that actually to get sigma hat, you need to take the median absolute deviation and use the appropriate correctional constant. you need some kind of correctional constant that depends on the CDF of a Gaussian, just to ensure that if there were no noise, your estimate sigma half would be an unbiased estimator of the underlying sigma from the actual distribution. So, what's amazing about this theorem, just to take a step back, is that it gives you the best of all possible worlds. So it's provably robust. You start off epsilon close to a Gaussian, and you actually do get some provably robust estimates. It's also computationally efficient because how do I compute the median and median absolute deviation? I just compute them. And in fact, it's also statistically efficient. If I wrote down the sample complexity, it would turn out that it's minimax optimal. It uses the optimal number of samples up to a constant factor. Okay, and now let me connect this to the way that I think about these problems in terms of terminology. So I'm a theoretical computer scientist, and what this would be called for a theoretical computer scientist is it would be called proper agnostically learning a 1D Gaussian. So let's break down that terminology a little bit. Well, it's called agnostic learning because you're no longer positing this religious belief that you really are given samples from a Gaussian distribution. Instead, you're getting samples from some distribution. And if it happens to be very well fit by a Gaussian, then you want to find a very good fit of a Gaussian. And in fact, it's proper for that reason, because we want not just something that fits the distribution we're giving samples to, but we actually want it to be back within our family. We want it to actually be a 1D Gaussian. I think that was the other question in the chat. And now I can get to what I really care about in this talk, which is, what about robust estimation in high dimensions? So this is a tutorial about high dimensional learning. And in the first part of the tutorial, I talked about how to use tensor methods to get algorithms for high dimensional learning. But let's talk about what happens when we deviate from those nice generative models. Is there a way to still do estimation in high dimensions in a computationally efficient manner, but in a way that we still have interesting guarantees when we have model misspecification? And in fact, one of the things you should think about is that there's all kinds of data analysis in high dimensions going on right now all over the place. You can think about some examples from genetics, like doing microarrays with 10,000 genes. The problem with doing high dimensional data analysis in these settings is that we really do have noisy data, but we don't know how to visualize these kinds of high dimensional data sets. So we don't even have a good understanding of how much the noise that's in these data sets is biasing the off-the-shelf estimators that we're using. And I think this is a major issue for science and engineering. These are just questions we don't generally know how to answer. It's kind of a dirty secret. All right, so now let me tell you some of the bad news. Let me tell you about the tension between robustness and hardness in high dimensions. This is something that we just didn't see happening in one-dimensional robust estimation problems, but is really something we have to tackle head-on in high-dimensional settings. So let me define the world's simplest robust high-dimensional estimation problem. So imagine we have the same exact problem, except we have a d-dimensional Gaussian. So we're given samples from a distribution that's not exactly a Gaussian, but it's promised to be epsilon close in TV to a d-dimensional Gaussian. Now, the difference is that here, the unknown mean mu is a d-dimensional vector, and the unknown covariance sigma is a d by d PSD matrix, right? But the goal is the same. What we want to do is we want an efficient algorithm that also takes only a polynomial number of samples, and it's going to spit out an estimate mu hat and sigma hat, so high dimensional estimates of the mean and covariance, with the property that the Gaussian that they define is O tilde epsilon close to the original Gaussian that we started from. So now let me make good on one of the promises that I made before, which is, in 1D, it really didn't matter a whole heck of a lot on how you define what it means for the parameters that you estimate and the true parameters to be close. But actually in high dimensions, it matters a whole heck of a lot. That's because if you think about how close do I want sigma and sigma hat to be, those are d by d matrices. So, do I want them to be close in terms of, I look at the spectral norm of sigma minus sigma hat? Do I want the Frobenius norm between sigma and sigma minus sigma hat to be small? Do I want some other norm? All of these different matrix norms, they often differ by poly and d factors. So you need to make sure that you choose the right norm. That's why it makes sense to work with total variation distance, because that characterizes what the adversary has done to your distribution. They move you in total variation distance, and you want to get within total variation distance again. So this is the way that this is the reason the problem is set up the way that it is. And now let me introduce just a little bit more nomenclature, because I'm going to dig into some of these problems and tell you what's known. So I could make your life easier in this problem and work with one of the following two special cases. So one special case is I could make your life easier, and I could promise you that the unknown covariance sigma is actually the identity. So it's a spherical Gaussian, and you just want to estimate the center of that Gaussian. So can you robustly estimate the mean of a high-dimensional spherical Gaussian? I'll call that the unknown mean case. Instead, what I could do is I could make your life simpler by promising you that the unknown mean is 0. And all you have to do is estimate the unknown covariance. So what the shape of this ellipsoid is for this ellipsoidal Gaussian. So what's known in the case of the unknown mean? So if you think about it, in the one-dimensional problem, we knew that the median was a good, provably robust estimator for the unknown mean. So the natural thing to try is to try and use a high-dimensional analog of the median. Well, that's exactly what Tukey did. So there's something called the Tukey median. Now, I'll preface this by saying that you don't actually have to know what the Tukey median is to understand the rest of the talk, but let me just tell you in words what the Tukey median is. Well, you can think about this point cloud of samples that you get from your distribution. And there's something called the Tukey depth of a point, which is if I take a point, I look at the worst case over all 1D projections about how close it is to the endpoint of the projections of all of these points. So the Tukey median is the Tukey deepest point. So it's the point that sits in the middle of the distribution, that no matter what 1D projection you choose, it's somehow sitting in the middle of all of the other projections. Now, the Tukey median would be great because, in fact, what's known about it is that if you start with something that's epsilon close to a spherical Gaussian, then the Tukey median will be such a good estimate, a robust estimate of the unknown mean of the distribution, that it'll actually get you epsilon close in total variation distance. But there's a big catch, which is that you can't actually compute the thing. So it's NP hard. In fact, what this means concretely is that if you have n samples from a d-dimensional point set, and you want to compute the Tukey median, the best known algorithms run in time roughly n to the d. So even though the Tukey median is very well studied in computational geometry in low dimensional settings, I have never seen it be successfully computed beyond dimension 6. So these kinds of high dimensional applications that we care about in a lot of modern machine learning are just way out of the reach of these kinds of estimators because you can't actually compute them, even though we do know that if we could, they would be provably robust. Now, there's something much more naive I could do. Maybe I just chose the wrong generalization of the median to high dimensions. So there's something really naive I could do, which is I could just choose the coordinate-wise median of the distribution. So I look at each of the the distribution projected on each of the coordinates, and I compute the median, and I stitch them together to get my high dimensional estimate. That's very obviously computable in polynomial time because it's just d different median problems. The trouble is that it really loses in the error guarantee. So you start off being epsilon close to a Gaussian, and you only end up epsilon times root d close back to the original Gaussian. This is not an issue that you see when d equals 1, but this is a major issue when you talk about robust estimation in high dimensions. And I'll talk a little bit more about that on the next slide about what is just so bad about losing this root d factor. But you can do this exercise for all of the estimators that have been proposed in the literature. Everything that has a great dimension-independent error guarantee turns out to come with this hidden gotcha that you can't actually compute the thing. So, in my field, in theoretical computer science, we love the phrase, the price of. So maybe this is just kind of the price of robustness, because all these known estimators, they're either hard to compute in high dimensions, or we lose some polynomial in d factors in our robustness guarantee. So what is so bad about this is that the total variation distance between two distributions is only ever at most 1. So the way to think about it is, how small do I need the fraction of corruptions to be in order to have any non-trivial guarantees on how good my estimator is? I need the fraction of corruptions to be like 1 over root d. So the fraction of corruptions needs to be plummeting to 0 as you go to higher and higher dimensions in order for these estimators to give you anything non-trivial. Even if you're thinking about a problem in 10,000 dimensions with no hidden constants in your robustness guarantee, this means that you can only tolerate something like 1% corruptions, even though we know in principle that it's possible to tolerate a much larger fraction of corruptions that's totally dimension independent. So at this juncture, you might actually wonder, is robust estimation even algorithmically possible? So there's another question in the chat, which is, can you switch from TV to KL? So that's a little bit of a technical answer. If you don't mind, I'm going to answer that at the end. So maybe remind me, because I don't want to get too sidetracked right now, but thanks for the question. So let me tell you about some recent results. I'm actually going to tell you about the first wave of results. And at the end of the talk, I'll tell you about really a flurry of progress in this area, and I'll give you a broad survey of it. So a couple of years ago, me and some great people, we proved the following result. There's an algorithm that takes a polynomial number of samples, which has the property that if you're given samples from a distribution that's epsilon close in TV to a d-dimensional Gaussian, it finds robust estimates of the high dimensional mean and covariance that get you O tilde of epsilon close. So there are no d factors whatsoever, not even log d terms here, and you can get truly dimension independent robustness guarantees. And the algorithm runs in time polynomial in n and d. So you can be both provably robust, sample efficient, and computationally efficient in these settings. So there really is something that you can do even when you deviate from these very simple generative models. And in fact, tensor methods are going to play a key role. Not Generics algorithm, but really the tensor structure of the generative model will still, be a very useful primitive in figuring out how to cope with corruptions in your data. So there are a few extensions of this work, and I'll talk about many more extensions later. But you can actually weaken the assumptions. You don't need the distribution to actually be Gaussian. You need merely that the inliers are sub-Gaussian or bounded second moments, albeit you get weaker robustness guarantees for things like mean estimation. At the same time, independently and concurrently, Lai, Rao, and Vempala gave the following algorithm for robustly estimating a d-dimensional Gaussian. So they managed to get mu hat as the L2 norm between mu and mu hat is roughly epsilon to the 1/2 times some extra factors that depend on the underlying covariance times a polylog ND factor. And they also got bounds on how close sigma and sigma hat are in Frobenius norm. Now you can translate these results to bounds on the total variation distance under some additional conditions on your distribution. It turns out that when the underlying distribution has a bounded covariance, what this really translates to is that your estimates are close enough that you're epsilon to the 1/2 close in TV to the Gaussian that you started off from. Okay, so let me tell you now a general recipe about robust estimation in high dimensions. In fact, these estimators are pretty easy and built on some general concepts that have since been applied to all sorts of richer models. So here's how robust estimation in high dimensions is going to work algorithmically. The first step will be that I want my estimates to be close in total variation distance. And what I'm going to do is total variation distance is a really ugly thing to work with. Instead, what I'm going to do is I'm going to find an appropriate parameter distance that's easier, that's sufficient to bound it so that I can get strong guarantees on TV. Then step 2 is we're going to do something a bit more naive. Instead of trying to design one estimator that works no matter what corruptions the adversary adds, what we're going to do is we're going to be adaptive. We're just going to use the naive estimator, the empirical mean, the empirical covariance, but we're going to figure out some clever ways of detecting when the adversary has compromised that estimator. And then what we're going to do is we're going to be able to find many outliers and purify our data by removing them. So that's basically how high dimensional estimation is going to work. So actually, let's see how this works in the simplest setting, which is the case where we just want to estimate the unknown mean and the covariance is the identity. So first, what's the right parameter distance for bounding the total variation distance between two spherical Gaussians? Now, for those of you who think a lot about different distance measures between distributions, and this ties into Clement's question earlier about what can I do with the KL, then it turns out that a good way to bound the total variation distance is to use the KL divergence. Because the nice thing is that the KL divergence between two Gaussians has a closed form expression. And through Pinsker's inequality, you can say that bounds on the KL divergence imply bounds on the total variation distance. Now, if you do this, what it tells you is it tells you this very nice intuitive fact that if you have two Gaussians with the same identity covariance, but they only differ in the mean, mu and mu hat, then the total variation distance between them is upper bounded by the Euclidean norm between mu and mu hat divided by 2. Now, this makes sense because really, when you have these two Gaussians that only differ in the mean, figuring out what their total variation distance is really a 1D problem because you should just take the line that connects mu and mu hat, and that's where all of the differences between the two PDFs arise. So I'm going to take this fact for granted, but this is how you prove it, is you invoke Pinsker's inequality and you use the well-known formula for the KL divergence between two Gaussians. But this means that we have a new way to formulate our problem. Our goal in the case where we want to robustly estimate the unknown mean is that we want to output a mu hat that's O tilde of epsilon close in the Euclidean norm to the true unknown mean. So this is our goal. So now let me get to the meat of how exactly these things are going to work. So how can we detect when an estimator, a naive one like the empirical mean, has been compromised? So let's think about this problem geometrically. So when we have a high dimensional Gaussian with identity covariance, then what happens is that your distribution looks like a high dimensional spherical ball. All of the distribution is really concentrated on a thin spherical shell of a ball of radius root d. And the center of that ball is at mu. So now how could the adversary really corrupt the empirical mean? Well, what they would do is they would add a bunch of corruptions right on the boundary of this ball, but they would concentrate them along some direction so that they have an epsilon fraction of corruptions, and the points at the boundary of this ball are root d away from the center of the ball, which is mu. So this epsilon fraction of corruptions can move you epsilon times root d away from the true mean that you'd started out at. So this unravels a bit about why the question is formulated the way that you are. See, if I hide for you the colors of these different samples, if I don't tell you which one is black and which one is red, you have no chance of figuring out which of the samples were inliers and which ones were outliers, because these red points will look statistically indistinguishable from the true samples if I do it right. And so instead, my goal isn't to detect which points have been corrupted and which ones haven't. It's merely to detect when the naive estimator has been compromised. In such a situation like this, I can hope to figure out, well, a subset of the points, which is much more red than black, which if I throw it out, I'm going to end up with an easier, robust estimation problem. So, how can I detect that my naive estimator has been compromised? Well, if I think about projecting all of my data along the direction that connects mu and mu hat, then this direction would actually have variance that's much, much larger than 1. So I started from an uncorrupted distribution, which is supposed to have variance 1 in all possible directions. But instead, by virtue of what the adversary has done to compromise the empirical mean, I have a direction of very large variance. So here's the key lemma, which I'm not going to prove for you. If you take samples from a distribution that's epsilon close to a Gaussian n of mu I, and you take enough samples, then if you compute the empirical mean mu hat of your samples, which come from, along with corruptions, and you compute the empirical covariance sigma hat, then what I claim is if your estimator mu hat is not good, if it's too far away from the true mean, if the Euclidean norm, the Euclidean distance between mu and mu hat is at least 100 times epsilon root log 1 over epsilon, then what that means is that there has to be a direction of large variance. that the spectral norm of the difference between sigma hat and I is at least epsilon times log 1 over epsilon. And so what's the main takeaway from this lemma? So what's the abstraction? Is that in order for an adversary to corrupt the empirical first moment, there actually needs to be some echo of what they've done in the second moment. And that's how you figure out where the adversary has added the corruptions. And now how can we put this all together to get our overall algorithm? Is we're just going to do a win-win algorithm. And the basic idea is, we're just going to use the empirical mean. And either that will be a good enough estimate on its own, or we're going to find some way to remove many outliers, many of the corruptions that the adversary has added to our data to get an easier, robust estimation problem. So, if we compute the empirical mean and the covariance is really close to the identity, then the converse of that key lemma I gave you implies that the estimate mu hat you have is actually close to the unknown mean mu. So what happens if sigma hat is not close to the identity and we know we're potentially in danger? So what happens if the spectral norm between sigma hat and identity is large? So in this case, the reason that the empirical variance is large along some direction must be due to the outlier. So if we take the direction of largest variance in sigma hat and we project the data along that direction, what we show is that there's some sort of threshold t, so that if you throw out all the points above this threshold, then you throw out many more outliers than inliers, because those are the ones that you have large variance along this direction. Now, some inliers do get thrown out along the way, but for every inlier you throw out at least, let's say, 2 outliers along the way. So eventually, even though in this first step you didn't get a provably robust estimate for the unknown mean, you're making progress because your data has gotten more pure because you've reduced the fraction of corruptions within it. And in fact, what's going to happen is eventually, if we continued for too long, we'd actually have no more corrupted points left to throw out. So this eventually finds certifiably good parameters. This is one of the reasons why we have to work with a strong contamination model where the adversary is allowed to look at the data and then decide what corruptions to add. Because, in step 1, even if you start from a nice model where the adversary is choosing their corruptions obliviously, after the first filtering step, you don't really have control over what your data looks like. Even the inliers are not IID necessarily from a nice distribution because of the correlations that are introduced in this filtering procedure. It turns out to be not super easy to prove that this algorithm really does work, but it can be done through the appropriate things, that you can actually get a polynomial running time bound and polynomial sample complexity. And yeah, I'm sorry, you guys are asking such good questions in the chat that, I'm always cognizant of the fact that if I actually answer them during it, I might break some of the flow for it because these are kind of technical answers. So I'm going to try and answer both Clement's later question and Anna's question towards the end, if that's okay. Thanks for the questions, though. And actually, the sample complexity bounds are based on what's called concentration of LTFs. All right. So now let's take this general recipe much further. So the unknown mean case is actually not super hard to do. You could have done it many different ways. The unknown covariance case is now when we're going to get into tensor methods again. So in fact, what we're going to do is we're going to follow the same general recipe. So remember our recipe for robust estimation in high dimensions is first we got to find the appropriate parameter distance. Let's figure out how to do this in the case where we just have an unknown covariance. So actually we do the same trick as before. We want some parameter distance that's good enough to bound the total variation distance between 2 Gaussians, which have the same 0 mean. And you do the same trick. Pinsker's inequality works. The KL divergence between 2 Gaussians still has a nice closed form expression. But what it gives you is this kind of funky expression right here, which relates sigma and sigma hat. And this is actually called the Mahalanobis distance. Our new goal is to find an estimate where the Mahalanobis distance is small. And actually, if you look at it, it kind of makes sense because, when the mean is 0, and you think about sigma and sigma hat, what this thing looks like is it looks like the ratio of the variances along different directions. And if you ever have a direction in which the ratio of the variances is very far off from each other, you can't be close in total variation distance. So when I asked at the beginning, what's the right distance function to use between how close sigma and sigma hat ought to be? Well, the answer was none of them. It's not to use the spectral norm. It's not to use the Frobenius norm. The right thing to do is actually use this Mahalanobis distance. That's actually the thing that's affine invariant if you look at it appropriately. And it actually is the right one in order to bound the total variation distance. So now let me just give you a flavor of how to do this for the unknown covariance, and we'll see tensor methods again come to the rescue. So what happens if we're given samples from a Gaussian n of 0 sigma? And I want to do the same thing I tried to do before. I want to use the naive estimator, the empirical covariance sigma hat. Now, this isn't going to work all the time, but at the very least, I want a method to determine when this naive estimator has been corrupted. So here's the key fact. So imagine you take samples from a Gaussian sigma, and if we're trying to detect whether the empirical second moment has been compromised, the natural thing to do is to use the fourth moment as a test. Now, the fourth moment would be a tensor, but tensors in some cases are actually hard to work with. The problem here we're talking about is not a tensor decomposition problem, it's something else. So instead, what we're going to do is we're going to flatten the tensor to create a much larger matrix. So the fourth moment of this distribution would naturally look like a d by d by d by d tensor. Instead, we're going to flatten it into a d squared by d squared matrix M, which is the expectation of x sub I tensor x sub I, all times itself transpose. So the key point is that this matrix M is actually very nice. Now you have to be careful because it's only nice when you restrict to the right space. But if you restrict it to operating on the right vector space, then actually it has this beautiful structure, which is, it looks like 2 times sigma tensor 2 times sigma flat transpose. Now I've just kind of invented what this flat symbol is. What it is it's a rearrangement of the matrix. So you take a d by d matrix and you rearrange it into a length d squared vector, and you take it times its own transpose. Now I'm not going to prove this fact for you. It's proved using something called isotyrolysis theorem or Wick's formula, which what it does is it relates the moments of a Gaussian to matchings. And it turns out that there's a relationship between the fourth moment of a Gaussian and matchings in the complete graph on 4 nodes. Now, what happens is that M really has 3 different kinds of terms that correspond to the 3 perfect matchings in a complete graph on 4 nodes. 2 of the matchings look like the sigma tensor 2, and one of them looks like sigma flat times sigma flat transpose. That comes from this asymmetry that when we flattened the thing and we think about pairing up the different copies of x sub I, well, if I pair up this x sub I in the outer one and these 2 right here, one of the pairings corresponds to the row and one corresponds to the column. And similarly, if I pair up this guy with this guy and this guy with this guy, one corresponds to the row and column. But this pairing is a little bit different because it pairs elements of the row space and this guy pairs elements of the column space. So that's the sense in which one of the matchings behaves differently. And this is actually a major problem because if I think about an adversary who's adding corruptions to sigma hat that really derails my estimator, somehow I want to look at spectral properties of M as a way to determine where the corruptions have been added. But the trouble is, imagine you look at this formula and you plug in sigma is the identity matrix. Well, if I take the identity, tensor the identity, that's still the identity. Its spectral norm is 1. Nothing's happening there. But if I take I flat times I flat transpose, that's a rank 1 matrix. And actually, its spectral norm is polynomially large in D. So there's a huge shadow for the adversary to add corruptions within. And that's where the adversary could hide unless you know how to project out this one term in exactly the right way. So it turns out that there is a way to project out this one term in exactly the right way. Actually, since I'm sort of short on time, I'm actually just going to assert it, but it turns out there's a way to set it up through restricted eigenvalue computations, that what you can show is that in order for the adversary to mess up the second moment, then they really do, there has to be some echo of what they've done in the fourth moment that you can detect through this restricted eigenvalue computation on this flattening of the fourth moment of the distribution. So you can turn this into an algorithm for the overall problem, because what you can do is you can first use a doubling trick where you take twice the number of samples, and if you look at the differences between them, those samples will look like they come from something close to a Gaussian. They look like something that they look like samples from a distribution that's O of epsilon close to a Gaussian whose mean is 0, because the mean cancels out and you've doubled the covariance. You can use the algorithm for the unknown covariance to learn sigma hat. Then you can apply sigma hat inverse to your data. That's like a kind of agnostic isotropic position. And then you can robustly learn the mean in this setting. And this turns out to be the right distance in which to estimate the mean, because if there's a direction of very small variance, that's a direction in which you'd really better get the unknown mean correct. And this gives you the overall algorithm for agnostically learning a high dimensional Gaussian with dimension independent robustness guarantees. So, after our work, there was actually a huge flurry of progress, so much that it's actually honestly hard for me to keep up with. So let me, in the last few minutes, tell you a bird's eye view of some of the exciting things, with the caveat that this isn't even all of the stuff that's happened. It's been kind of amazing how much stuff has happened. So one of the questions you might wonder first is, we gave algorithms which got O of epsilon times polylog 1 over epsilon guarantees. And you could ask, is it possible to get O of epsilon? So that turns out to be computationally hard, at least in the sense that we can prove lower bounds for a natural family of algorithms called statistical query learning algorithms. That's only true in the strong corruption model, where the adversary can do insertions and deletions, that these things, in order to beat epsilon root log 1 over epsilon, must make a super polynomial number of queries. Actually, the intuition for this is really simple. If you think about where epsilon times root log 1 over epsilon comes from, is, how could an adversary move you not just the mean by epsilon, but epsilon times root log 1 over epsilon? Is if you take a 1D Gaussian, the adversary could cut out one of the tails. And when they cut out the tail, that would move you by epsilon times root log 1 over epsilon, even in 1D. So in order to avoid losing that root log term, you would have to notice that you're actually missing a tail and fill in the tail. So somehow algorithms that beat this epsilon times root log 1 over epsilon, they would have to be very brittle in a different sense, that they would have to very strongly rely on the structure of the uncorrupted distribution and exactly what the tails look like in order to figure out that's what the adversary had done. You can also ask different kinds of questions that tie in with other areas of theoretical computer science. You could ask, what happens when an adversary corrupts not, at most 10% of the data, but 90% of the data? So what happens if the adversary can corrupt a majority of the samples? The first time you think about this question, it seems like you can't really say too much that's interesting, because, an adversary might, if they could corrupt 90% of the data, well, you might get samples from a Gaussian, and then they might add a bunch more Gaussian components that are just as heavy as the Gaussian you started off from, and you would have no way of actually figuring out which was the true original Gaussian. So in this case, what Charikar, Steinhardt, and Valiant showed is that you can solve the problem in a list decoding sense. So you can output a small list of hypotheses with the promise that at least one element of the list really is provably close to the estimate through the unknown mean that you started off from. And there have been various improvements on these algorithms that get better improved guarantees, although under stronger conditions. So you need not just that the covariance is bounded, but under some kind of Gaussianity or other higher bounded moments assumptions. There are also notions of, relaxing distributional assumptions. Some of this we did in our original paper, but a really beautiful line of work was really completed in this Kothari, Stoyer, and Hopkins-Lee papers, where they showed tight bounds for, what level of bounded moments you want to assume. If you assume that you have bounded kth moments, in fact, you need a slightly stronger condition that not only are the kth moments sub-Gaussian, but you need that there's actually a low degree proof in the language of sum of squares, for the sub-Gaussianity. Then you can actually get these kind of error guarantees. As you have more and more moment information, the estimator improves in the sense that it approaches this optimal epsilon dependence. But in fact, when all you know is that you have bounded moments, this epsilon to the 1 minus 1 over k type of dependence is actually the best that you can hope for information theoretically. So this is a really neat line of work too. Another paper that I really like in the space is a different take on robust estimation, which is what happens when there aren't corruptions, but instead you have heavy-tailed distributions. So in that case, if you didn't have heavy-tailed distributions, you could just use the empirical mean, like if you get samples from a Gaussian, and you would get very, very narrow confidence intervals. But when you have heavy-tailed distributions, it turns out to be much more subtle in order to how to get very tight confidence intervals. So a really nice work of Sam Hopkins showed how to do this, actually using sum of squares to get nice Gaussian type confidence intervals. The important thing is that what it outputs is an estimate mu hat, that this confidence interval, the width depends logarithmically on whatever delta, where delta is your failure probability. And there were earlier approaches, like the approach of Lugosi and Mendelssohn, that showed how to get these types of confidence intervals, but inefficiently, based on something called the median of means estimator. Some of the ideas that I described play some kind of conceptual role in, for example, Hopkins's work, and even some of the later improvements which gave faster algorithms based on gradient descent. So let me stop there. So let me tell you what I hope that you got out of the talk. So really, we started from this question about what happens when we don't have a nice generative model. It turns out that even if you take the world's simplest generative model, a high-dimensional Gaussian, which no one would ever ask, can you learn a high-dimensional Gaussian? The answer is, duh, of course you can. You get very interesting questions when you ask, can you learn it robustly? And actually, there are approaches based on ideas from tensor analysis and restricted eigenvalue problems. So, some of the same actors that we saw last time that can give you provably robust estimators that marry robustness with computational efficiency in interesting ways. I give you some other applications to other kinds of generative models and related problems. And I think there's there's a lot more to be doing in this space in algorithmic robust statistics. Just to give you a little bit of a preview about what I'm going to talk about next time, you can think about all the problems that I described today as really being unsupervised learning problems. What I'm going to discuss tomorrow will be robustness in the context of supervised learning, where again, there's going to be this funny business that, there are a few ways to define what your corruption models are. In the context of supervised learning, there are going to be some interesting quirks about which kinds of corruption models are just too computationally hard to work with, and which other ones really are the right compromise between both having strong corruption models and leading to actual algorithmic guarantees. So I'll stop there. Thanks for your attention, and I'll answer any questions you guys might have. I see a few questions in the chat, so I can start there.
Thanks, Ankur. And also, if you have a question, you can feel free to raise your hand, and we can unmute you to ask it live.
Okay, so Clement's first question that I haven't answered is, does the error guarantee tend to O of epsilon if you let n go to infinity or even more? So no. So actually, they really do get epsilon times polylog 1 over epsilon. So in the strong contamination model, we had a later follow-up paper that actually improved the guarantees in robust mean estimation and got epsilon times root log 1 over epsilon, which is the thing that matches this SQL lower bound. One of the funny things is that you can go back to the Huber contamination model, where remember, you're not allowed as an adversary to delete points from your sample. You're only allowed to inject new points. And in those kinds of injection models, you actually can get O of epsilon for the robust mean estimation, because you can't do this trick of like deleting a tail. So that's kind of cool that there are actual genuine differences, not only between which robustness models are stronger than others, but even what you could hope to achieve in terms of computational complexity. So that I think is kind of neat. And there is some genuine barrier for some of these models. Then Anna asked, is there a sense in which some adversaries are complete for a class of adversaries, or is it possible to do reductions between adversaries or tasks to perform on the corrupted data? I'm not sure I have a really meaningful answer to that one, because even very close by adversaries that seem to be pretty closely related, I don't know how to literally relate the two. So, when I talked about one view of the corruption model as the adversary gives you samples from any distribution that's epsilon close in TV to the distribution you started with, that looked like an adversary who, one, had to choose obliviously which data points to corrupt without looking at the rest of the sample. So they have to choose their strategy. And the way that their strategy is constrained is that in expectation, it has to add not too many corruptions. Even slight variance of these kinds of things where, where you're allowed to not be oblivious and actually look at parts of the data. I don't know how to relate those back to the original model. So it's kind of interesting, but to be honest, I don't have any religious reasons for why one corruption model is the right one compared to the others. It's honestly more that the reason we worked with a strong contamination model was a strong corruption model was because in our analysis, we had to. So after the first step of the filtering approach, well, in principle, the adversary could have added corruptions in a way that the inliers that you throw out had some weird statistical relationships amongst each other. And then in the second step of your filtering algorithm, the remaining inliers might have some weird dependent structure on each other. So then, the adversary is somehow like the corruptions that are left over don't look like any kind of nice model with the data that's left over. So just by virtue of the analysis of the algorithm, it seemed necessary to work with these stronger corruption models. But that's a very good question. Next question is, for Gaussian mean estimation with unknown covariance, can we learn the mean with optimal rate in linear and D number of samples? That is, without first robustly estimating the covariance. Okay, so first, optimal rate. So, there are a few interrelated questions here. So I guess, because the unknown mean case, you can't hope to get O of epsilon, at least under computational considerations. I'm interpreting your question as, can you get roughly close to epsilon, O tilde of epsilon? And can you do it with the information theoretically minimal number of samples? Now, in the case where the covariance is known and it's the identity, then actually we do have algorithms, which I didn't describe, which are based on semi-definite programming that do the trick. But in the case where you don't know the covariance, I don't actually know the answer to this question, because what's funny is that in order to learn the covariance well enough, within, let's say, Frobenius norm, you need D squared samples. So that's already a D factor larger than you need to learn the mean in the known covariance case. So I think that's a very interesting open question, and I don't know. It's a nice question. Oh boy, there are a lot of questions. All right, so next one from Clement, again, is does anything change at all if you ask that the adversary be efficient as well? That's an awesome question. This is sort of more thinking like a cryptographer, that a lot of times that's how you make a huge amount of progress in crypto, is that your adversary isn't an arbitrary information theoretic adversary, but is one that is computationally bounded. I've never actually been able to make much sense of that in the context of learning. Just to connect this with some of the things that I talked about last time, there are many different adversaries you could imagine. Here we had ones that are computationally unbounded. And, the things that I talked about, even for like learning mixtures of Gaussians last time with tensor methods, why do you expect the mean vectors to be linearly independent is because if you perturb them, then they would be. So I like thinking about smooth analysis as a good way to limit your adversaries. I like to think about it, I guess this is still recorded, but I'll say it anyways. I like to think about it as an adversary who's a little bit drunk because, he moves and his hand tremors. And that for me has been a very powerful way to curb the power of the adversary, is to make him drunk, like smooth analysis. But I've never seen ways to do it based on constraining the adversary's computational complexity, except in some somewhat more specialized models. But I would be happy to learn of counterexamples. Okay, so the next question is, so how about the improper case where your goal is to just come up with some distribution that's close in TV to the original? Presumably that's easier because the corrupted distribution is already close to the ideal. So I don't actually know any examples in which that's easier in a high dimensional setting. So improper learning tends to be much, much stronger in low dimensional settings, even for classic learning problems. Like if I want to in 1D learn a mixture of k-Gaussians, we don't actually know how to do this in better than exponential and k time with proper density estimation. So where I want to output something that really is a mixture of k-Gaussians that's close in TV to the underlying distribution. But there's a really trivial way to do it with improper learning, which is what you can do is you take a bunch of samples from your distribution and you convolve it by a small Gaussian that smooths the density function, and that'll work. So there are already some examples of where this can be really beneficial in low dimensions. I've never seen it successful in high dimensions for some of the basic estimation tasks, and there are actually lower bounds for a lot of those problems. And one of the issues is that imagine in the context of robustness, hypothetically, that you could improperly learn something that's close to the original distribution. Well, that's still only close to the original distribution. It's like 2 epsilon close to the original distribution. So the task then of finding, something that really is from your family that's now close to that thing that you've learned, I don't know how to solve that problem because it sounds like almost the same robust estimation task as I started with, if only for the fact that because I have a description of the hypothesis, I don't actually need to take more samples. So that kind of thing would be really beneficial to make sure that you don't take too many samples, but still this computational question of searching within the space where you merely have very good 10% agreement rather than arbitrarily small agreement seems kind of tricky to me. Now, Bryce asks, you present examples of a heuristic, try the naive statistic, detect when the naive statistic has been corrupted, then fix the naive heuristic. And the detection step looks at deviations of the naive statistic. Is there a formalization of this heuristic, or is it done ad hoc each time? This is done sometimes a little bit ad hoc because there's some bias in the examples that I presented for you, which is that these are all examples in which there is a nice parameter distance that bounds the total variation distance. Now, when you talk about learning more sophisticated generative models, like mixtures of general Gaussians, there isn't actually a nice parameter distance that in all cases is sufficient to bound the total variation distance with dimension independent guarantees. Some of the learning algorithms based on tensor methods, based on the method of moments, things that I'd worked on earlier, those give you parameter distances that are polynomially related to the TV between two hypotheses, but with dimension dependent factors. So that's actually one of the things that goes wrong. And there's been a lot of progress that I didn't even have time to talk about in this talk on robustly learning mixtures of Gaussians, which design some kind of, very clever, but, things that are a little bit ad hoc in the sense that they work for various special cases of mixture models that have nicer ways of controlling, when different hypothesis classes are close to each other. So they can sort of carve out some space of the set of hypotheses you want to learn and figure out that these are settings in which you do have a nice parameter distance. In fact, Daniel Kane has a pretty amazing work that solves the thing for mixtures of 2 Gaussians that invents some parameter distance that only Daniel Kane could dream up. But anyways, I encourage you to check it out. It's pretty neat. I think that's all the questions.
Yeah, it looks like all the questions. There was a question that I thought that you would address that you maybe just now sort of addressed that I had dismissed a little bit earlier. Let me see if I can dig it up just because I want to give it due diligence. Sorry.
I think this was a question, are there robust estimator results for Gaussian mixtures?
Right, yeah, that's the one.
Oh, sorry, could you say it again?
Are there robust estimator results for
mixtures?
Yeah, so there are now somewhat, in the sense that there's 2 works at Fox, I think, that were merged, which were very nice, which study the question in the special case where the mixture of k Gaussians has the property that all of the components are pairwise far in total variation distance. So then you can get nice, provably robust dimension independent guarantees. Now, one of the things that I do want to point out is that these things tend to, if I remember correctly, not get O of epsilon or O tilde of epsilon closeness, but they get epsilon to the omega 1. So think like epsilon to the 1/6 or something like this. So even though there are very strong guarantees in that setting, and that is a setting in which that's the setting in which you most often want to learn a mixture of k Gaussians, is when the components are actually pretty distinct. In those kinds of settings, you can get provably robust things, but there's still nice questions about improving the dependence on epsilon. In fact, I see a question in here who might be one of the authors in the paper from Ainesh. Yeah. In the case where the mixtures are clusterable, you can characterize TV distance in terms of parameter distance. Exactly. So that sort of fits in with one of the other questions that I was addressing, that in that special case of mixtures of k Gaussians, which admittedly is one of the most interesting cases, that's something where there is a nice parameter distance that actually relates to TV. But, for mixture, and so Daniel Kane has a recent work which gets the same epsilon to the c types of guarantees for mixtures of two Gaussians with almost no assumptions. The only assumption he needs is that the mixing weights are the same, which is kind of a bizarre assumption. Probably someone could remove that, or you could try and improve the epsilon to the c type of dependence. But no one knows the full answer for mixtures of k Gaussians yet. But you can ask these questions in all of your favorite generative models, and these are beautiful, important, very, very, very hard questions.
Yeah, sorry, just to add one thing to that list of open questions, the running time that we get is also like d to the k to the k. And it's a great question to understand whether you can improve it.
Great, thanks.
Okay, so if there are no further questions, then let's all thank Ankur one more time for this fabulous second installment in his series, and we'll go to the coffee break in the Gather Town. Thanks.